Greetings, Earthlings. Well, today we're going to look at this. This is a Valhalla Scientific 2500 AC/DC current calibrator. And what is that for? Well, now, you remember we've got this HP 34703A that I'm trying to restore. And if by some miracle I should get it to work, it has, it can measure current, very low level currents. It has a 1 microamp full scale range up to 100 milliamps full scale. And so how do you calibrate something like that, right? This has a 1 microamp full scale to 1 amp full scale, which should prove useful. The way this works is you put a voltage in, 0 to 1 volts, and 1 volt is the full scale current that you have selected. So currently, like, I have the 10 milliamp button, and if I put 1 volt in, I should get 10 milliamps out. In the past, I've used this thing, which I built myself, and what I've done is just compare readings with the meter I'm testing and my Tektronix DMM4020, which I know is pretty accurate. But you see, if we look at the settings on this thing, it's currently set, well, it's reading 12.2 milliamps, right? But this is reading 12.146. If I adjust it, there's quite a range here of 12.2. So the actual 12.2 is in there somewhere. But it's hard to get there. And then going down to very low level currents. Well, there's, it says 1 microamp. And this thing doesn't even really go that low. What's 1 microamp look like? 0.001 milliamp. So that's showing 5 microamps. Not really practical for calibration, for proper calibration purposes. So this will be better. Let's take a look at it. Input voltage, output current. It's got an on-off button, and it's got a range selector, and it's got a 0 adjustment there. Tilting it up. Not much there. Last calibrated in 2000, so it's a few years old. Turning it around, looking at the top, there's nothing there but screws to get inside, and the back, there's nothing there but the power. Okay. So let's power it up and see if it blows up on us. Input will come from the Fluke 343A, which I deem to be accurate. Whether it is or not, it's my reference. So in this space, it's assumed to be accurate. Okay, powering on. It comes on, and I have 0 volts in, and so that's showing what? 10 microamps? 10 microamps. Yeah, 10 microamps, something like that. Let's give it 1 volt in and see what we get. That's pretty close. Now, I just turned this on. It hasn't warmed up. Wow, that is pretty close. It hasn't warmed up. Ambient temperature reads 20 degrees Celsius. Let's go to half. 0.05. Well, okay, so that seems off. 10 volt. 10 volts? Oh, yeah, okay. Oh, I'm sorry, I went the wrong way. Yeah. Its maximum output is 10 volts. Let's see. if I go 100 milliamps, I'm back at 0. That's 1 volt. Yeah. 0.1. Yeah. It's close, but it looks like it needs to be calibrated. It's 1 volt. Yeah. And that can take 3 amps, so I should be able to go to the 1 amp scale. Give it 1 amp. Look at that. Yeah, again, it's off by a little bit, so I should let it warm up. I should get the room temperature up to like 23, which is where things normally get calibrated. And I should look at calibrating it now. But it does seem to work. Did we get lucky? I don't know. 100 microamps, yeah. 10 microamps, yeah. Oh, and of course it was 0. Yeah, that needs to be adjusted. So in terms of actually calibrating it, how do you do that with something like this? If you don't have, a reference meter that can read to more digits than you need to read. This claims, what does it claim? I forget the number. I'll put it on the screen because I'll look it up. And I'm probably not going to get it that close, but the way that you actually calibrate this thing is by having precision resistors, okay? And we give it 1 volt in, and on each range you would use the appropriate value of resistor that would give you 1 volt out, right? So at 1 amp, that's a 1 ohm resistor. 10, 100, 1,000, 10,000, 100,000, 1 meg at 1 microamp. I have all of those to about 0.01% precision, so we're going to get it in that range. Like I said, I think that it's advertised accuracy is better than that, but that's about the best I can hope to do here. But yeah, basically you feed it into a known standard resistor, and then you use the null meter. Remember the null meter? Our old friend, the null meter. we use the null meter to measure the difference between the input voltage and the output voltage at the resistor. And when those match, if we assume that the resistor is 100% accurate, right? When those match, then the current output is, exactly what it, what it's supposed to be, right? So we put 1 microamp into 1 mega ohm, we should get 1 volt out. We have 1 volt in, we have 1 volt out. Boom. Anyway, that's where I'm at with that. It seems to be in quite good shape, so doesn't really need much except a bit of a calibration. So perhaps like I said, we'll let it warm up, and maybe we can try and run it through that. All right, it's continuing to warm up. Let's have a look inside. Might as well. There are 2 screws here on this panel, and then 4 screws on this, I'll call it a retainer. This lifts off. This is scary. That lifts off, and then this will lift off, and that's all we need to do to get inside. Big honkin' transformer, 1998, okay. Big honkin' capacitors. Looks like 93 date codes on those. That's weird. And then here's the actual circuit with some precision resistors here, and these are the adjustments. There's 1, 2, 3, 4, 5, 6, 7, 8, it looks like. Schematic looks like that. Whoops, it looks like that. And I've highlighted all of the adjustments. Well, there's an AC adjustment too. I'm not going to worry really about AC at this point. Then the procedure. Now, the procedure that they specify, I'm going to have a problem with. So they want 0.003% resistors, and for the load resistors, these switchable ones can be worse tolerance, and then they say accurate to 0.01%. Okay, so they've got a factor of 3 in there. This is 3 times better than the accuracy. Now, generally you go do better than that, but it's hard enough to find 0.003% resistors. In fact, I'm not sure I have any. Well, these standard resistors might have been when they were made 0.001%, but they have probably drifted with age. I'm going to assume they're accurate. But here's the thing. There is one adjustment, and it is, let's see, R54, which they call the compliance adjustment, where they want to do it on the 1 amp range. So switch a 9 ohm resistor in series with the 1 ohm resistor. Now, I have a 1 ohm standard resistor, and it can take an amp, not to an accuracy of 0.001%. It was, let's see, it was 0.002%, it looks like, from the factory. And it was, whenever it was measured, 1975, 0.99994.5 ohms at 25 degrees C. It's not 25 degrees C. I've got a thermometer here. This is kind of a room temperature range thermometer. It goes from 66 to 80 degrees Fahrenheit. That's an ASTM 17F. 66 to 80 degrees. And it's showing 73.2 degrees right now. It's the temperature of this resistor. Whatever that translates into in Celsius. I'm measuring it on the Fluke 8500A, and the Fluke is reading it at 0.9986 ohms. But I don't know how accurate that is on that scale. It's actually the 10 ohm scale on that one. It has a temperature coefficient as well, these resistors, and it's like 8 parts per million per degree C. It says +8, but I noticed that the readings are going down as the temperature goes up. The resistance readings. So it doesn't seem like that would be a positive temperature coefficient. I have to think about that one. Anyway, I'm letting all the heat out of this. I can feel heat. But a big honking linear power supply. And then, there's a couple of op amps, precision op amps, and some precision resistors. And that's basically the whole circuit. I am going to move this out of the way so I don't spill, break that thermometer and spill mercury all over the place. I am going to tilt this back down. Okay, you can see the shorting bar there. I'm going to cover it back up. I'm going to try to zero it. I shall attempt to turn it. That's the wrong direction. Well, there's 0. Okay. Yeah, that's going to be close enough. Okay. There's the return current. Okay. Current flows through the resistor. We're comparing rather, the voltage at the resistor against the voltage at the input. And it says get it within 100 microvolts, which is full scale here, and we are well within 100 microvolts. So oh, I see. All right. Yeah, they agree. Okay. I call that good for the 1 amp. Okay. So now here's the 10 ohm. And let's see where we got. Okay. And this will be the next. This will be this one. This seems out by quite a bit. Oops, because I'm turning it the wrong way, maybe. Go on 100 microvolt scale and say that's right in there is close enough. Okay. All right, so after all my fiddling around, I think I've got it pretty much calibrated. Probably good enough for my purposes. You know, I've got like 4.5 digit stuff that I'm trying to calibrate here. Best case, 5.5 digits. I've checked it against the Tektronix. It's pretty close. But here's a fun thing. This Keithley 171, okay, which I did sort of calibrate to the best of my ability some time ago. It has a 1 microamp range on the low end up to 1 amp. So this is a perfect, this is just a perfect test here. 1.0005. So this is on the 1 microamp scale. Full, full 1 volt in. 0.1 volt in. 0.2. It's less interesting down at this range, but that's pretty close, okay? 5 counts. I call that good enough. Let's go to 10 microvolts. Whoa. 10 microvolt range. And we'll switch to 10 microvolts here. 10.004. Okay, that's pretty close. This should be 1, 2, 3, 4, 5. Now you notice also that with nothing in, it had, well, let me just completely disconnect, okay? I didn't bother to zero that. So with nothing in, it's reading 0.002. Or 2 counts. So the best we could hope to do is so you can subtract off 2 counts and say we're that much closer. So 10.002 is the actual reading here, which is pretty darn good. Okay. 100 microamps. Again, pretty close. Let's go to 1 milliamp. I'll take it. 10 milliamps. Not bad. Not as good, but not bad. Go 100. Go to 100. 100.07, 0.08. Yeah, that's as bad as the other one. Wait a minute. I wonder what our 0 point is here. Well, it's one count, so. Yeah. Again, that thing, it's been some time since I've even attempted to calibrate that. So I trust this more than I trust that, really. And we go to 1 amp on the 1 amp scale. 9996 milliamps. That's pretty good. Can that take more than an amp? I don't really know. If I go back down, this can actually, yeah, okay, good, overload. This can actually exceed, a 1 volt input. So if I go to a 2 volt, it's specified 0 to 2 volt input. Okay. Well, it sure didn't like that. It sure didn't like that. Did I blow something up again? No. It's fine. Let's go down to like 1 milliamp here. Range. And I'm on the 10 milliamp range there. I should be able to get, well, depending on the, the resistance of the shunt resistance in the meter, because this has maximum of 10 volts output. And you notice here, maybe you can see this light is coming on, the overload light. That doesn't mean it's in overload. That just means the readings may be suspect, and you should check, which means maybe you get your voltmeter out and check the voltage. But in any case, that is reading 2 milliamps there, so it's quite functional. So I mean, I'll use this as my current reference and be happy with the results. If I adjust whatever meters I've got to match this, at least they match each other, and it's good enough for my purposes.